we're given this power source and there's a sensor a distance away, and we're looking to find the magnetic component of the light wave, the time derivative of that at least, and actually the maximum of it as well. It might be a good idea for us to just kind of start there. So the component of the light wave is supposed to be the B max times the sine of kx minus wt. And if we take the time derivative of that, then we would just basically multiply it by this thing and also take the derivative of the sine. So we'll get bm and then cosine of kx minus wt. And then there's also this negative w thing that we have to multiply this by. But we're looking for the maximum, so technically the cosine stuff is just going to go away. So we'll see that the maximum of the time derivative of the magnetic component is just going to be w b max. So all we need to do is figure out what w is and b max, and we should be able to get this. Well, w is going to be equal to 2 pi and then the speed of light divided by the wavelength. That should be part of our little equation sheet. And then for the bm, the b max, well, that we have this other thing that we could say would be the E max divided by the speed of light. So I suppose we have to find E max. And we could find this thing pretty easily, so let's just do that. We'll say 2 pi, and then we could divide that by the wavelength, which is 510 nanometers, and then we can multiply that by the speed of light. So the wavelength is just going to be 3.715 rads per second, I suppose, which is fine. So we have this. That's the angular frequency, at least. Okay, so now we want the Emax. Well, Emax, we're given some other information in this problem, this stuff here, so let's use that. Because we know that there's this thing called intensity, and that's just equal to the power source divided by the area, 4 pi d squared, where that d is the distance from the sensor there. So we have I equals 210w divided by 4 pi and 450 meters squared. So we can figure out what the intensity is. Let's just do that real quick. So we got 210 divided by 4 pi times 450, and then we'll square that. So we have that I is equal to 8.25 e to the negative 5. And this is technically in watts divided by meters squared. Well, now let's look at the other equation for I, because I is also equal to ERMS squared divided by the speed of light times mu naught. So we should be able to solve for ERMS with that. Take a look at that, times the 3 and the 8, and then times mu naught is 4 negative 7 times pi. So ERMS, at least the squared, is going to be that. Let's go ahead and square root that. So that ERMS is going to be equal to 7 over 15. And Emax divided by square root of 2 is ERMS. So let's multiply this by square root of 2 to get the Emax. All right, so Emax is equal to square root of 14 over 15. Now we can plug it in there. Let's divide that by 3 to the 8. So we have our Bmax. So Bmax is equal to 8.3 e to the negative 10 Tesla. And now we can multiply it by that. And now we have the final answer. So d over dt of bz max, that's going to be equal to 3076474. And this would be like Tesla over seconds. It's crazy.